Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen the circuit for the array multiplier or the combinational multiplier. So using that circuit, we can multiply the unsigned binary numbers. But in the real world, we are also dealing with the negative numbers. So in this video, let us see how to design a multiplier circuit which can multiply the signed binary numbers. So in the earlier video, we have already seen the multiplication procedure for the signed binary numbers. So in case of the signed binary numbers, we need to extend the sign bit of the each partial product up to the 2n bits. And we have also seen that in case of the signed binary multiplication, we need to subtract the last partial product. That means the multiplication of the signed binary numbers consists of two additional steps. That is the extension of the sign bit of the each partial product up to the 2n bits and the subtraction of the last partial product. So the subtraction of this last partial product is equivalent of taking the 2's complement of this last partial product. So here the same thing is shown for the 3-bit numbers. So as you know, taking the 2's complement of the number is equivalent of taking the 1's complement of the number followed by the addition of the 1. So for the last partial product, the same thing is shown over here. So as you know, for the 1's complement, we need to replace zeros by 1 and 1's by 0 in the number. So basically, we need to complement the each bit. And then this 1 is added to get the equivalent 2's complement number. So in the earlier video of the signed binary multiplication, I have mentioned that we need to take the 2's complement of the last partial product only when the multiplier is the negative number. For example, we need to take this last step whenever this multiplier b2 b1 b0 is negative number. But this method will also work even if the multiplier is positive. So if the multiplier is positive, then this bit b2 or the MSB of this number will be 0. So in that case, all these bits, that is a2 b2 dash, a1 b2 dash and a0 b2 dash will be 1. That means at all those positions, we will have 1 1 1 1. And when we add 1 to it, then all the bits at the corresponding positions will become 0. And this 1 will get shifted to the P6 position. So here we can ignore that bit, because here we are only concerned about the first 6 bits, that is from P0 to P5. That means in this method, whenever the multiplier is positive, then this B2 bit will be 0, and because of that, this last partial product will get vanished. And therefore, this method will work even if the multiplier is positive or the negative. So now let us see how to implement the same thing in the digital circuit. So if you want to implement the same thing in the digital circuit, then compared to the unsigned binary multiplier, here we require the additional hardware. So for the 3-bit unsigned binary numbers, we have seen that we require the 3 half adders, 3 full adders and the 9 AND gates. But in case of the signed binary multiplication, since we need to extend the sign bit of the each partial product, so we also need additional full adders. So here, this is the circuit of the signed binary multiplication of the 3-bit numbers. So as you can see over here, for this sign extension, we require these additional full adders. Apart from that, for adding this 1, instead of the half adder over here, we require the full adder. And apart from that, to complement these bits in the partial product, instead of the AND gate, here the NAND gates are used. So in short, for doing this signed binary multiplication, we need the additional hardware in terms of the adders. And as the number of bits in the number increases, then we require the additional hardware. But with the little modification in the circuit, we can avoid these additional adders which is required because of the sign extension. So let us see that. So here, once again, the multiplication of the 3-bit signed number is shown. Now in this multiplication, at the 3 different locations, the 1 is added and subtracted. So if you see over here, then in the 3 different columns, the 1 is added and the subtracted. So overall, the multiplication will remain the same. But because of this operation, now this additional sign extension bits will get vanished. So let us see how. So first of all, let us see this 1 which is added with the A2 B0. So if the A2 B0 is equal to 0, then after adding the 1, the result will be equal to 1. That means at this position, we will have 1. But since the A2B0 itself is equal to 0, so all the sign extension bits will be equal to 0. And since they are 0, so there is no point of writing them. On the other hand, let us see the same thing when this A2B0 is equal to 1. So if the A2B0 is equal to 1, then after adding this 1, the sum will be equal to 0 while the carry will be equal to 1. That means now at this location we will have 0 and this carry will be forwarded to the next stage. So once again in the next column, this A2B0 is equal to 1. Therefore, this 1 plus 1 is equal to 0 and there will be a carry of 1. And once again, it will be forwarded to the next column. So once again in the next column, this 1 plus 1 is equal to 0 and 1 will be the carry. So once again, it will get forwarded to the next column. And once again in the next column, this 1 plus 1 is equal to 0 and 1 will be the carry. But now if you see, then this carry will be at the P6 position. But here, since we are only concerned about the first 6 bits, or in general for the first 2n bits of the multiplication, so we can ignore this P6 bit. So as you can see, even if the A2B0 is equal to 1, then also after the addition of the 1, all the sign extension bits will become 0. And since they are 0, so there is no point of writing them. So in general we can say that when we add this 1 to this A2B0 bit, then irrespective of the value of this A2B0, all the sign extension bits will get vanished. Moreover, after the addition, this A2B0 bit at this position will get inverted. Because as we have seen, if this A2B0 is 0, then after adding this 1, the result will be equal to 1, which is the complement of the A2B0. And similarly, if this A2B0 is equal to 1, then after adding this 1, the result will be equal to 0, which is once again complement of this A2B0. That means in short, this A2B0 bit at this position will get inverted. And similarly, with the same logic, when we add 1 to this A2B1 bit, then all the sign extended bits will get vanished. And this A2B1 bit will get inverted. Similarly, when we add 1 to this A2B2 bar, then the sign extended bit will get vanished. And this A2B2 bar will get inverted. Now here, this minus 111 is equivalent of minus 0111. So if we take the 2's complement of this number, then this minus sign will get converted to the plus sign. And as you know, the 2's complement of this number is equal to 1001. So of course over here, while performing the 2's complement, we are considering the bits only up to the P5 location. Or in general, we are considering the bits up to the 2nth location. So now, when we add 1 to this 1001, then the result is equal to 1010. So basically, in terms of the hardware if you see, then we need to add the 1 at the P5 and the P3 locations. So now, if you think in terms of the implementation, then we need to invert these 4 bits and we need to add 1 at these 2 locations. So this is the modified circuit of the 3-bit multiplier for the signed numbers. So as you can see, to invert these 4 bits, instead of the AND gate, the NAND gates are used. And here, to add the 1 at this P3 location, instead of the half adder, the full adder is used. So if you recall the 3-bit multiplier for the unsigned numbers, then at this location, we have used half adder. But here, to add this additional 1, we have used full adder. And similarly, using this additional half adder, this 1 at the P5 location can be added. So in this way, by using the minimum additional hardware, we can use the same multiplier circuit for the signed numbers. So similarly, this is the circuit of the 4-bit multiplier for the signed binary numbers. So basically over here, we need to complement all the A3BI and the AIB3 bits except when I is equal to 3. That means here, this A3B0, A3B1 and the A3B2 are complemented. Similarly, this A2B3, A1B3 and A0B3 are complemented. So for example, if we have a 5-bit binary multiplier, then each binary number will have 5 bits. So in that case, we need to complement all the AIB4 and the A4BI bits except when I is equal to 4. So here, in case of this 4-bit binary multiplier, all the 6 bits are inverted. And after that, we need to add the 1 at this n plus 1 and the 2n locations. So for this 4-bit multiplier, starting from the LSB, we need to add the 1 at the 5th and the 8th location. That is the n plus 1 and the 2nth location. So here, this 1 is added at the P4 and the P7 location. So in the previous video, we have already seen the circuit for the 4-bit multiplier for the unsigned numbers. So to use the same circuit for the signed number multiplication, these 6 AND gates have been replaced by the NAND gates. So basically, they will invert these 6 bits. And to add the 1 at the P4 location, instead of the half adder, the full adder is used. Because if you recall the circuit of the 4-bit multiplier for the unsigned numbers, then at this location we have used the half adder. But here, to add this 1, we have used the full adder. And similarly, to add the 1 at this P7 location, this half adder is used. So in this way, with the little modification, the same multiplier circuit for the unsigned numbers can be also used for the signed numbers. But like I said in the previous video, in this array multiplier circuit, as the number of bits increases, then the required amount of hardware resources will also increase. And therefore, it is not suitable for the large multiplication. And for that, other types of multiplier circuits are used. And the one common multiplier circuit is the booth multiplier. So in the future videos, we will also see that. But I hope in this video, you understood how to design the combinational multiplier or the array multiplier circuit for the signed binary numbers. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.